This conference will now be recorded.
All right. Hello, everyone. Brian Gockel here, Weather Service Office of Observations. Sitting in for Jordan Girth today, who's got a very, very tight schedule, some schedule conflicts. You are in the right place, though. This is the Satellite Book Club weekly seminar series, and great talk lined up with you today. Chris Schultz is going to be presenting. The title is Fusion of Remote Sensing Datasets to Anticipate Lightning for Impact-Based Decision Support Services. Just a few introductory comments. You probably heard the prompt. This session is being recorded, so folks who can't make it today can listen in. As usual, we'll have Q&A after the presentation, and we are appreciative to have Brian Curran back to the Satellite Book Club, the Sue from WFO Midland Odessa, who will be the facilitator today and will be handling our Q&A. And before we get started, want to always put that friendly reminder in. We're always looking for future presenters. So if you have a topic related to exploitation of satellite data, whether alone or in conjunction with other observational or non-observational data types, we always welcome presentations. Please contact the TOWRS team. Contact information will be provided. And the training team is always available. Brian Mata is the focal point for development of briefing and training materials that might not yet be available. As always, thanks to the TOWRS team, a virtual collaboration of Office of Observations, GOES-R, JPSS program offices, and OCLO and other interested and involved stakeholders. Thanks to Kashad Bowman of the TOWRS team for putting these materials, helping us put the materials together today and get our script straight. Want to introduce Dr. Chris Schultz, our speaker today. His focus is on understanding the kinematics and microphysics that drive extreme lightning flash rates and convection and their applications to monitoring severe weather, snowstorms, wildfires, and volcanoes. Chris works for SPORT and the atmospheric electricity teams down in Marshall and in Huntsville. And he's also part of the GLM and International Space Station Lightning Imaging Sensor, ISS-LIS, science teams. And he's a member of the National Lightning Safety Council. Chris, thanks for coming to the Satellite Book Club. Welcome. We look forward to hearing your brief. The floor is yours.
Thank you, Brian. Thank you, Brian, and I appreciate everyone who has helped make this happen, Kashad, Jordan Girth, Scott Rosowski, and several others. So today's talk is really about trying to be proactive in our lightning decision support. And I'm going to introduce a couple of new techniques that I've been thinking about and working with our local emergency management here in Huntsville, as well as the local WFO here at NWS Huntsville. And so to begin, it says I want to leave the meeting. Hold on. I'm trying to go forward. There we go. Okay, so to begin, I'm going to prompt you with a couple of things that I'm going to talk about today. And one of them is use of more than one lightning observation and the remote sensing that's accompanying those to diagnose a situation. And I want to get you to think about getting away from the apples to apples comparisons of flash rate now that we've got multiple lightning data sets available in the operational community. You've got Earth networks, you've got VISLA, you've got some cases you got lightning mapping arrays that are being used by certain offices. And of course, you've got GLM. And so the other piece is talking a little bit more about how there might be different techniques needed to anticipate lightning for, initiation and then cessation, as well as, stratiform and anvil situations versus, say, more of a convective type application. So those are the two main things that I'm going to speak to today, and I hope that it resonates with you and we can have some good discussion after. So the whole thing, my whole thing here is, why can't we just use flashes? And the real reason is because if you go by the true definition of flash, there isn't one. It's all defined by how measurements are made. And so something that's in the VISLA or networks flash rate would be different from something that's in GLM or an LMA or something that we might see in person. And so it all comes down to how how the lightning's measured and what part of the lightning's being measured, because lightning emits across the electromagnetic spectrum, and you could have optical properties, you could have things related to the leader as it propagates to the cloud, and you can have things related to the electromagnetic pulse that it generates, which is how VISLA and Earth networks kind of triangulate positions to get you those accurate locations of ground strokes. And so that's where I want to start your frame of reference here. And to move on, you know, we have several types of lightning observations that are used operationally. The most notable that most of you are all familiar with is the NLDN or Earth networks. These are time of arrival systems that use the electromagnetic pulse that lightning generates to then triangulate the position using multiple sensors. Strengths, you can really accurately detect cloud to ground lightning and some in cloud. The weaknesses, you don't really have any spatial context of how big the lightning is. We know visually that lightning isn't just this one point at a certain location, and that it has some spatial context. When you come to optical lightning mappers like GLM or the Space Station Lightning Imaging Sensor, you do get accurate two-dimensional mapping of the footprint of that lightning feature. The negative is you can't tell if it came to ground or stayed in the cloud because of the limitations of GLM. It's a two-dimensional plane on the top of the cloud. And so that main weakness is you need to know exactly where those cloud ground strokes are, especially for applications for safety, or even in case of wildfires or things like that. Lightning mapping arrays do accurate three-dimensional mapping of lightning. It's almost like taking an X-ray of a lightning flash in a cloud. You know exactly where the lightning went. You know how the height of it. You can even infer some charge information that could be relevant to the convective state of the cloud. The limitation here is that they're very, very limited in range. They only go about 125 to 200 kilometers, depending on the networks that are out there. And there are several out there, but they're very, very small postage size stamp areas that you're able to use these data. And then even more rare are the electric field mills and field change mills that are operational at some of the main spaceports like Kennedy or out at Vandenberg, where they're trying to understand the electric field prior to that lightning occurrence to make sure that they can get their equipment in as safely as possible. So I touch on each of these in the hopes that you can remember some of the strengths and weaknesses. And ultimately what I'm going to talk about is how when you go to take the initial approach of what data set do I use, you try to match up the strengths and weaknesses of each of those different sensors to maximize your ability to observe the phenomenon you're trying to support with decision support. So the reason why it matters is because not all of those lightning sensors will see the lightning in the same way. And so this is a IDSS example from here in Huntsville. It was during the Panoply Arts Festival, which we have about 30,000 people on any given day in an outdoor venue downtown. And so what we have displayed here is lightning mapping array data in the colorful dots, and then the diamonds are National Lightning Detection Network data. And if you go by the National Lightning Detection Network data, there are a few points farther south of Huntsville, but nothing within 50 kilometers. Meanwhile, the lightning mapping array data is showing the extent of the lightning flash that was detected by the NLDN, and the footprint shows it going over Panoply, over Redstone Arsenal, which also has an airspace, and Huntsville International Airport, which would then trigger an airport weather warning. And in this specific case, there were 7 of these flashes that traveled over the same area during a 1 hour period. And so without the combination of the data, you would hear the forecasters would hear the rumbling overhead while they're at Panoply, but not be looking at the scope, be looking at their real-time data and be wondering why they're not detecting it. And so again, you want to try to fuse something that's got that good cloud to ground and in cloud designation information with something that maps. And so I'll touch a little bit about the importance of lightning IDSS. From the Safety Council standpoint, we know that the majority of lightning injuries and fatalities occur prior to the storm arriving or just as the storm has moved away. And we know that often it is not raining. And you guys are familiar with this in your interactions with the public. with emergency management and your partners. The main thing that I want to reemphasize is that some of these techniques that we'll talk about today might help give you that confidence to really hit home that, hey, yeah, there's that lightning risk. But anyway, the main reason I'm bringing this up is that we do have this. We had this problem a couple years ago here in Alabama, where one of my friends, Tommy Self, was at a baseball field and happened to notice this lightning flash occurring with crowds of kids and parents just meandering about, not really paying attention to the storm because it wasn't raining yet. And so the goal here is to try to be a little bit more proactive with some of these approaches, so you can message and hopefully be able to message to your partners about the threats and even message to the public. So one of the other points I'm making today is separating convective and stratiform lightning IDSS. And the main reason is that there are two physical mechanisms that generate charge and lightning. In panel A there from Bruning and McGorman, what you see is more of a slab of charge. And what that represents is the way that a broader, a little bit weaker updraft would generate charge in, say, a stratiform region, an anvil, or maybe even a snowstorm in the mid-latitude range. And so what happens there in panel A is you get slower charging rates. You need bigger fields to then generate the lightning. But when that field does go, it's a big, bright flash with multiple cloud ground points. And so while they be infrequent, they are really important. And we had a case 2 years ago, or 3 years ago now, in New Jersey, where this type of situation was present during a snowstorm, and a middle school teacher was hit while directing car line, trying to get everyone out as the heavy snow fell. Panel B is more of that convective updraft, where you've got smaller pockets of charge due to the turbulence. If you think of like the cauliflower nature of a cloud, when you have that cauliflower nature, you're able to lower the electric field needed to generate a lightning flash. And so you can get more frequent flashes that are smaller in size and dimmer in optical intensity. And so the reason is you're closer to that source region of how charge is separated through non-inductive charging, and you're able to replenish that electric field much quicker. And so there are two different things I'll talk about here in the next couple of slides. One will cover that convective part, and one will cover the stratiform region and some approaches that we've been implementing here in Huntsville that might be applicable to where you are. And so for initiation's been a problem and a challenge that's been studied for quite a while. And the main thing for initiation, there's a radar component and there's a satellite component that you can utilize to anticipate that first lightning. And a lot of the work goes back on the radar side, goes back to the mid to late 90s, talks about reflectivity thresholds at certain temperatures. You need to have that mixed phase region to generate enough electricity to generate a flash. And so a lot of the thresholds that, say, Gramillion and Orville discussed back in their paper in 1999 are still pretty applicable today. And now with the applications that we have with dual pole, you can add in that information about where grapple might be available. So use the hydrometeor ID and the dual pole to really hone in even further, not just is this reflectivity meet that temperature and reflectivity threshold, but is there grapple present? And what Preston and Fuelberg show in their WAF paper is that when you have those two things co-located, your probability of a flash really increases. There have been several satellite-based methods as well. And so there's the Sims group at Wisconsin. There's a group down here at UAH that has used cloud top cooling, the 3.9 channel, and being able to understand when glaciation occurs. And with the recent addition of RGBs, there's been an approach by the Jacksonville office to use a combination of the day cloud phase RGB with the lightning to really gain a couple precious few minutes with their partners, especially on the coast, of when lightning might be possible in these, especially in the summertime storms. And so what we see here in Elsenheimer and Gravel's paper from WAF, they use a combination of the day cloud phase RGB, and what they're looking for are the growth from green to more of an orange to anticipate when that lightning occurs. And they have a really nice schematic showing how once the cloud is able to reach above the 0C isotherm, you're able to start generating that cloud, and how the colors change within that the RGB to anticipate that first lightning. And so this would be, if you haven't already, I know several offices are already familiar with this work, and if you haven't, I would highly suggest you looking at it, because it is a really robust method that I'm going to talk about here a little bit later about how we're going to test it this summer a little bit more rigorously. So after that convective piece, we have the stratiform piece, right? And often you'll see as an MCS moves through, or say if you got an anvil of a supercell and it starts generating these big, large flashes, how do we really anticipate lightning out of this? Especially the reflectivity part here, that there's sometimes you'll have charged regions within this reflectivity area, and sometimes you won't. And so what we've been working with a lot recently here in sport is trying to quantify how, using some of the methods that have been around since the mid-90s or even earlier in some cases, but trying to operationalize them, trying to get them out in the operational community to see how well they work for you and the needs you have. And so this is the case from April 19 of 2020. We sat in the stratiform region up here in Huntsville, which is up at the upper end of Alabama. We sat in the stratiform for a good 3 to 4 hours. And then about 6:25 p.m., big 8-second rumble. My kids were scared, but at the time, Brian Carcioni immediately texted me. He's like, "What was that?" Well, we went back and looked. And so when we went back and looked at the radar data, there were signs that that precipitation region was electrified. And so through the use of depolarization streaks, which are essentially when you have ice crystals that align vertically in the electric field, it'll change the scattering the electromagnetic wave of the radar and allow it to show positive streaks that are down here in the red circles or red ovals. And those were present 44 minutes prior to that first and only big lightning flash that occurred. And so what we've been working a lot lately, especially in these anvil and stratiform situations, is when are they present, and how long are they present, and how often do they produce a lightning flash? And that's work that's to be done, but we want to see how well these things work elsewhere as well. And so we've been working with Brian Carcioni and a lot of the Huntsville office to quantify here locally. But one of the things I want to put out to y'all is to try and start looking for these things. And there's plenty of literature out there that I can provide at a later time, or provide the satellite team at how we're thinking about these might be useful for IDSS or airport weather warnings or any other applications you have. Because when you have these streaks, they match up really well with where the lightning went. And then when you combine the GLM here in the blue, this I'm showing flash extent density, with the NLDN or Earth networks, you see that you can really connect the dots spatially. You see a spatial width of these radial streaks, which are well correlated with that area that was present for within the flash extent density, and where all the clouded ground points came. And so in total, this one single flash had 11 different clouded ground points. 7 were positive, 4 were negative. And so that's a whole, and a couple of them were, thankfully they avoided the airport radius here, but they were all around it. And so you might be asking yourself, well, Chris, how do we know that these are electrified, these streaks are electrified? Well, we have aircraft data that we've been working with from various NASA field campaigns. And this is an example from the IMPACTS campaign, which is ongoing across the Northeast US and the Midwest for snowstorms. We're flying the NASA ER2 above the cloud, and the NASA P3 with a bunch of probe information inside the cloud. And what we're seeing is where we have these streaks. In the red here is where we also observe electric field from the aircraft. We have some electric field mills on the ER2, and as we pass over these streaks, we constantly see the magnitude changing. Furthermore, when you go in and look at the P3 data, and bear with me on the right here, or on the left here, because the main thing I want to show is supersaturation with respect to ice, meaning that there's enough supercooled liquid water to cause riming, which if you look on the right, these are all probe data information from 1 minute, and you see a number of rimed aggregates, meaning that we are riming large aggregates. We are separating charge, because when you rime and you have collisions between larger aggregates and small ice crystals, you actually exchange small amounts of mass, which is the reason why you separate how you separate charge. And then in the updraft, the lighter ice crystals will go aloft, the larger aggregates will stay lower, and that's how you get two different charge regions in a cloud, and then the lightning occurs in between those regions. So our main point of this is that we're seeing that a lot of these things are indeed electrified, and the microphysics are supporting the theories that have been around for a long time. So before I walk through a case study, I want to also make you aware of there are some fakes out there, especially now that there's lightning data and radar scope and the ability to measure things. What has happened in the last few years as the technologies improved for the ground-based networks, they're trying to squeeze out as much data as possible to provide you as much information as possible. But sometimes the algorithms that they use don't converge on great solutions, and you'll get these cases where you have lightning that's several hundred miles away from the closest convection. And what happens here is that that triangulation piece didn't produce a great solution when they use the ellipses to track things down. And you probably will see these on social media, or might even be heard. You might even hear from some of your partners like, hey, what's going on here? Why do we have this lightning flash? There's nothing overhead. Just be aware of them. They might come up in your social media feeds or from your local media outlets. In this case, the process that we've been using with Jason Jordan and Joey Patton and Dailo Zhang and several others is to go back. We look at multiple lightning data sets. So we go back and we look at GLM or the other data set. Say if it was VISLA, we look at Earth networks, and then also look at the anvil and IR brightness temperatures. You need to have at least some cold cloud overhead to support something like this. And in this case, from the April, I believe it was early April in southern Alabama and Mississippi, what happened was there was no anvil. The brightness temperatures were too warm for lightning. They were near 273, if I recall correctly. And there was zero GLM or Earth networks information. So you could pare things down and determine whether or not the signature was real. But sometimes it may be real, right? And so this is a case where near St. Louis, Missouri, where there were multiple flashes that were a good 30, 40 kilometers out away from the closest surface precipitation. And so when you walk through, you double check with the GLM. Now you see a distinct path from the storm over Phelps County, Missouri, that propagated northeast into St. Charles, Missouri. So it lines up with the lightning data within radar scope or from the NLDN. When you go in and look at the data, while there's no surface precipitation, the dot is where the furthest cloud to ground strike is. The orange slice is the vertical cross section here on the right. When you go back and piece things together, there was anvil overhead, there were depolarization streaks, and you even see, it's a little hard on here, but we do have a paper in WAF that you can go look at a higher resolution. You see localized enhancements in reflectivity. And work done at University of Oklahoma with Stephanie Weiss, Kristen Calhoun, Don McGorman, and several others have indicated that when you see those smaller enhancements in reflectivity, your potential for cloud to ground activity, when you see them aloft near the freezing layer or melting layer, you have an enhanced potential for cloud to ground activity. And so when you look at the vertical slice, then you see this really nice long anvil that's to the northeast of all the convection to the south that leads right to that, that cloud to ground point. And so I invite you to look at the WAF paper. We worked with the Weather Service office in St. Louis. We talk a little bit about the day cloud phase RGB as well, and just kind of gathering some of our thoughts on how to tackle this very infrequent situation. So to summarize, and I'm trying to stay on track here, to summarize, the main things are try to maximize 2 different lightning systems when you're doing your lightning IDSS. Try to pick one that's got some spatial context, and try to pick one that's got that in cloud and cloud to ground designation, so you can match the 2 up and really try to diagnose what's going on in the atmosphere. And think about the convective versus the stratiform situations when you're going to make your decision or support a decision-making process. You know, the convective part will have grapple. You probably, when during early convective states, grapple reflectivity thresholds work really well. The cloud top cooling glaciation features that you should be familiar with by now are really key. And then also in most situations when you've got those isolated storms that don't really have a lot of anvil, once the grapple tends to go away, your lightning potential really decreases. And that's what Preston and Fuelberg talk about both on the front end and on the back end. And that stratiform anvil place, you really want to look at for those depolarization streaks and those enhancements in reflectivity near the melting layer. Those are your keys that the cloud, 1, has the ability to support the lightning, and 2, there's potential for cloud to ground activity based on the work that we've done. And again, these are techniques that we've developed with a little bit of operational flavor to them, and we're interested in seeing how they might apply to other regions, because we also know that across the country, the microphysics change a little bit. You have larger warm cloud depths in the southeast versus, say, in South Dakota or North Dakota, where you're basically going very limited warm cloud depth and you go straight into the verge around processes. So anyway, these are 2 of the takeaways that I recommend. And finally, we are doing a day cloud phase RGB assessment, working from Cindy and Chad's work. And what our goal is to see how the technique that was developed within Jacksonville's office and within their WFO is similar and different from determine similarities and differences for across the country. And the main thing I want to point out is, especially on the GLM front, I'm showing this, this figure up on the upper right. As you go further away from nadir, from the nadir of the GLM instrument, there's a lower detection ability of the storm, and it has to do with how the CCD, the instrument, is designed. And so one thing that we want to see is just make sure that we're communicating that there are some instrument differences as well as some storm differences that you're probably hearing about. You know, large hailstorms, GLM doesn't really detect very well, but this detection threshold information really could affect that early detection or that late detection, depending on how things are working. But their period assessment has started. If you'd like to get involved, reach out to us. Anita Leroy, Chris White at the Weather Service in Huntsville, and then myself are all points of contacts, and we're running essentially an assessment. We have a training. We're able to, we have a Google form. You go about doing your normal shift work, and then you provide a little bit of feedback at the end of your shift, whether some of the similarities and differences and things you might have noticed, or if you didn't even use the technique at all. So reach out to us. We've already talked with several of the regional SSD chiefs, as well as individual folks. So with that, I will remind you of Lightning Safety Awareness Week and take any questions, which I see 5 of them.
Thanks, Chris. This is Brian Curran. I hope that people will stay on for the discussion, and there'll be a survey link posted in chat. If you could fill that out and give us your remarks and opinions and such, that'd be most appreciated. I want to remind everyone that a week from today, on Thursday, June 10th at 12 p.m. Eastern Daylight Time or 1700 UTC, Joel Torres, Research Associate 2 and JPSS Satellite Liaison from CIRA, will discuss JPSS fire monitoring capabilities for NWS users. I also would like you to contact the TowerS team, specifically Lee Byerly and Kashad Bowman, for questions about the Satellite Book Club or for configuration of satellite products. They've been very helpful to me. More information will follow in an email from the TowerS team. And with that, I'd like to get into some questions. The first question that we have here is from Joseph Patton. He asks, do we notice a change in those polarization streaks on radar before and after the lightning flash? Is the flash reorienting these ice crystals very quickly whenever it finally discharges?
So thank you for the question, Joey. What happens is, what the theory is, that when you have a big lightning flash, you'll see the depolarization streaks the magnitude of them minimize. So you're releasing that electrical energy, and through time you'll build back up. One point I didn't make is that the reason it doesn't really work in a convective situation for depolarization is the time scale at which you need to build the charge to be measured by the radar. The radars, especially aloft, are at what, 5-minute cadence sometimes. And so you won't really be able to see those small subtle changes in an elevation scan within the convective pieces. But what typically does happen is you see some relaxation, but depending on how whether the charging mechanisms say you've got a strong convective line at the front and it's convecting charge rearward, you can replenish that charge really quickly. Or if it's a decaying anvil, you'll probably see something that's more like the field will relax and then not recover. And so at some point you'll be able to determine when the signal is no longer there. But that is also research to still be done too.
Thank you, Chris. NWS Sioux Falls asks a question that is also, I think, pertinent for a lot of Weather Service offices that use GO16 data. What is the best way to account for parallax with GLM data when trying to determine how close lightning may be to an IDSS event?
Right, so that is a tough question. I had a slide in here and I didn't want to go too long. The first point I want to make here is that when you talk about the two different measurements, they're designed to triangulate at two different locations. So inherently there is a parallax. The ground-based networks, they try to triangulate to a surface, and the GLM tries to understand where the cloud is at cloud top, or the lightning is at cloud top. So inherently there's a 15-kilometer bias unless you're really under nadir, no matter what. Especially up in the Sioux Falls area, the challenge is that you start getting that area of the light coming out of the side of the cloud. But the main thing is that the ground-based network should be equatorward of GLM locations. And the standard reference we tend to use is within 50 kilometers. I know that's huge, but right now there's work being done to make the GLM information more seasonal versus the rigid, like 15 to 20 kilometer cloud top, so that in the winter you're not overshooting things. But I know that it's not exactly the answer, but I would say as long as you're less than 50 kilometers, and the closer the better.
Okay, Chris, thank you. Derek Hodges has a question. When you say look for enhancements in the reflectivity near the melting layer, do you mean above, below, or at that layer?
I mean at that layer. So you'll have your melting. The way that the idea is presented is that you have large aggregates that are melting and maybe evaporating just below the melting layer, especially when it's not precipitating. So I'm talking about the non-precipitating anvil or the non-precipitating stratiform when I'm talking enhancements and reflectivity. Right at that melting layer, you should see smaller enhancements, 30, 35 dBz, as larger aggregates melt and then evaporate with time. But what that's demonstrating is that there is a downdraft there and that there is potential to launch a leader down to the surface.
So if I'm understanding right, the greatest charge separation will occur right below the melting layer, is that correct?
Right, and yeah, that's right, Brian, because what you're doing is you're getting a differential fall speed, and so you're separating the charge there as the aggregates are melting and the ice crystals are still aloft.
Cool. Chad Gravel has a comment for Southern Region WFOs. If you're interested in participating in the experiment, feel free to contact Anita, Chris. The Southern Region Science and Technology Support Division supports this initiative. I did see the email today, Chad, and I've already forwarded it to my staff, and I hope we get some participation. I have a question. How does your research affect the IDSS messaging of the 30-30 rule that lightning safety groups have advocated for years?
So the research, the vision here is, so we've got a vision within sport, and we're taking it a step at a time. The vision is to increase lead time on the front end and reduce downtime on the back end. We know that in some research we've done with the lightning mapping arrays here in Huntsville and with some GLM data, that 98% of the time, and this is based on both GLM and LMA data, when you have a lightning flash and you wait for that period of 20 to 30 minutes after that lightning flash, say if there's no lightning in that last 10 minutes, 98% of the time there isn't another lightning flash. But we also know that situations like the big stratiform MCSs where lightning is so infrequent that you might be able to message. So the vision here is be able to reassure your partners that they can one, they're making the right decision on the front end, but at the end, maybe saving time and money and being able to open things back up a little bit earlier on the back end. Because if you look at things like the FAA or even the US Air Force, they use different metrics. Now, I'm not gonna, we've looked at the different metrics, and you have to accept some level of risk. Say with the FAA criteria of 10 minutes and 6 nautical miles, we observed that 10% of the time there was another lightning flash after that 10-minute period elapsed. And so it all comes down to the partner and their needs and their comfort too. And so that's our goal here, is to try to enhance on the front end, trim on the back end.
Yes, I did a little IDSS with our AA ball club here in Midland on Friday. They actually went into a lightning delay based on what we were seeing in GLM, which was finally we're seeing some of our training coming through, especially in the baseball world, where obviously there's some problems we've seen in the past. We have a little more time, a few more minutes. If anyone has any questions, feel free to chime in or put them in chat. Going once, going twice. Okay, I guess I'll turn things back over to Brian Glockle for his final remarks.
All right, terrific. Thank you very much, Brian Curran, for returning to the Satellite Book Club and your very capable fielding of our Q&A here today. Very much appreciated. Thanks also, Chris, and this is on behalf of everyone, thanks to Brian and Chris. Chris, thanks for that informative brief. Very valuable. The bit about the depolarization streaks was new to me. I'm sure all the attendees walked away with something new today. So very valuable. Thank you, Chris.
Yeah, thank you for the opportunity.
You bet. And as Brian alerted us just a little earlier, informed us, I want to reiterate the invitation he extended to next week's Satellite Book Club. A week from today, we'll return at our normal time, where Jarrell Torres will brief us on the JPSS fire monitoring. And it's just about that time of year, or very soon will be, if not already, for some parts of the country. So with that, this concludes today's Satellite Book Club. Thanks for everyone's participation and attendance, and have a great Thursday afternoon, and we'll see you next time. So long.
Later.